Hello everyone, welcome to this video. Today we're going to see how to know if our statistical model is reliable or if it's good, using some metrics that are commonly used. So let's get started. The first thing that we have to answer is why the evaluation metrics even matter. Because when we build a model, accuracy alone isn't enough. We need to understand how well the model distinguishes between classes and how well it behaves with the errors. They simply help us answer, is the model really learning the pattern, or is it just guessing? And if it's good at identifying the right positives and negatives. Also, is there a trade-off between precision and recall? So let's get started by a simple example so we can better understand this. So we have some actual and predicted data. The actual data is given in advance from the data set that we have, and the predicted is are the model's predictions. So from the table we can extract 4 imported variables that we're going to use: true positives, true negatives, false positives, and false negatives. Each one, for example, true positive predicts if the model predicted 1 and it's actually 1. True negative if the model predicts 0 but the actual value is 0. When we say 1 or 0, it's not like positive is good, negative is bad. It's just a convention that positive class means the event that we want to detect. Negative is the event that we don't want to detect, or it's the absence of the event. This convention originates from the signal detection theory and medical testing. Positives, the test detects the condition. Negatives means the test does not detect the condition. So yeah, it's just a universal convention for clarity and consistent computations. But what if we have multi-class classification? For example, we're classifying images, cats, dogs, horses, or 0, 1, 2. How we can evaluate the metrics per class. For example, for each class, we get the true positives if the model predicts dog and it's dog, and it becomes false positive when the model predicts dog, but in reality it's not a dog, so it's either a cat or a horse. Then we can compute the precision, recall, F1 score for each class. So back to the example. The first thing that we're going to do is build the confusion matrix. It's just like what we've seen before, true positives, false negatives, false positives, and false negative. Let's check, for example, true positive, we have 2. It's when we predict 1 and the actual is 1, so 1 and 2. False negatives, when we predict 1 but it's actually 0, so it's this one, and so on. And now the first metric is the accuracy. It is the proportion of all classifications that were correct, whether positive or negative. It's true positives plus true negatives divided by everything. In the example it's 3 over 5 or 0.6, and then with this we can say that the model makes correct predictions 60% of the time. Now for the recall sensitivity, or we can also call it true positive rate. It's the proportion of all actual positives that were classified correctly as positives. So it's true positives divided by true positives plus false negatives. In the example it's 67%, so we can say that the model captures 67% of all the real positives. And now for the area under the curve and the ROC curve. It's a little bit complicated, but we're going to explain it So the area under the curve measures how well the model separates positive and negative classes, depending on regardless of the threshold that we have to know in advance. It comes from the ROC curve, which plots the true positive rate on the y-axis and the false positive rate on the x-axis. And we know the formula for the true positive rates, and this is also the formula for the false positive rates. So this is a conceptual formula. It's equivalent to the probability that the model ranks a random positive higher than a random negative. Let's see the example to better understand. Here, the predicted probability, it means like for whether a customer will default or not default. So we don't just output 0 and 1. The model doesn't do that. It basically says, in this first example, we are 90% sure that the client will default. So then we compare all the positive and negative pairs. We compare 0.9 with 0.8 and 0.2, and then we compare 0.6 the positive with all the negative, 0.8 and 0.2. So we have 3 correct and 1 incorrect, and so the AUC is 75%. We can also, this is the what we said, the false positive rates and the true positive rates. In the interpretation, when it's closer to 1, we have a better model. In this case, it's perfect model. If it's 50%, we can say that the model has no discrimination, it's random. Poor, if it's below 70%, below 80 is fair, or it's good if it's under 90% but didn't yet reach the 100%. So yeah, that's it. It's an easy but important subject. The metrics reveal how the model performs, not just if it's right. A good model depends on the problem. Like for example, in fraud detection or medical tests, recall and the area under the curve may matter more than the accuracy. So we have to know the problem that we have, not just like program or write a code for randomly using everything. But we also need to combine the multiple metrics for a complete performance picture. So that's it. Thank you for watching. Please subscribe and leave a like.